Okay, this is a review session for all the thermodynamics chapter. So from 10, 11 to 12. Generally, we expect one question lah. Okay, so this is a chapter where if you're kind of like running out of time and you don't have time to study everything and you generally just don't really like the ideas here, it's a okay question to burn. Like, never mind, it's okay. I'll focus on other stuff with more marks. So this one I expect maybe generally one question, um, perhaps two, but seldom. Okay, so generally it's one question. So we are looking at the ballpark of 10 marks to 12 marks. Because if they ask two questions, right, there will be one short question. So it's around 10 to 12 or upwards to 14, lah, but no more than that. So it's one question. But there are many ideas here. And the ideas here are not complicated, especially if you are used to thinking about gases. Okay, so if you're used to thinking about little particles, they travel quickly in all direction, colliding with each other, blah blah blah. So if you see the world and you think about it that way, then this is just a very natural extension of your knowledge. But we're going to start off with different types of past year questions first, starting with temperature. Okay, this is a cold chapter. Get the pun? Cold. Meaning it's not a very popular topic lah, all right? But the not nice thing about CIE is whether it's popular or not, if they ask, then you have to answer. So technically you have to know everything, which kind of sucks, but well, A levels, you know. So this one for temperature, the main point here that we need to know is the type of thermometers. So you don't need to know in absolute detail like in the lecture videos. We tell you extra because when you know extra, for some people knowing extra help them remember better. At least for me lah. But right now, if it's like the eve of exam, then you don't need to know so much extra already. You just need to know roughly the types of thermometer, identify them. You know the difference between thermodynamic and absolute scale, the Kelvin scale, how to calibrate and linearize, and what's the difference between temperature and heat. So the if you don't know how to read the reading, go and ask Miss Ellie or talk to us lah. We will help you clarify the reading. But it's okay, the writing, I mean. So here I'm going to show you some questions. All right. And if you haven't done any past years yet, you should focus on maybe if you really want to do the chapter, then the chapter that involve temperature, which is a few of it lah. So these are chapters that involve thermometer alone, like for this one. And I think this one we have already recorded, so you should go and watch it. Okay, Winter 11 Paper 4-3. All right. So the questions are always, I will go up and show you a calibration one. So this is a calibration question. They are very rare. Okay. So when they ask for thermometers, right, for example, they will say things like, explain what is meant by the statement of two bodies in thermal equilibrium. Okay. What thermometer should be used to measure the flame of a Bunsen burner? What thermometer should be used to measure the temperature of a small crystal when exposed to the pulse of ultrasound? So for this, all of this, right, I think a better way to do this is I'll just dig up a comparison for thermometers for you lah. Okay. And then you operate from there lor. All right. And then I'll do one calibration question. Then we'll move on to the second main idea. All right. So the first main idea is this lah. Types of thermometer, how to choose thermometer, and also how to calibrate thermometer, which I will choose a question from to discuss. Let me dig up the thermometer comparison table. A handy dandy one that is from the textbook. This one is oftentimes a blind spot for most students because it's a short chapter, so we will teach it very, very close to AS. So that if you don't remember also, never mind lah. Maybe it won't come out. Okay. But for your benefit, I'm going to put it here to not disturb the mind map. Okay. So these are type of thermometer. You should know the thermometric property. I'm not going to go through them one by one. You can read yourself. And then the advantages and disadvantages. I already went through one by one in the recording video. All right. So because of this, maybe there's 1-2 mark. You select the right thermometer. So let's think about the Bunsen burner flame. The Bunsen burner flame, right? You cannot put a liquid in gas mercury thermometer because the liquid in glass, because the glass will probably explode. If you heat glass directly, glass will crack and explode. So normally we'll put a resistance thermometer or a thermistor. Thermistor thermometer is not really that, but a resistance thermometer is better. A thermocouple is better. Okay, so look at the advantages and disadvantages. That's what you need to know. Okay, and when it comes to temperature scale, all right, again, just to, I got this from the Oxford book lah. All right, so understand that the thermodynamic scale is Kelvin. Okay, so our thermodynamic scale relies on the fact that it does not depend on the physical properties. All right, and I think this topic is no longer included in the new syllabus. Okay, because all this is like facts, and we prefer you to think about questions that you need to analyze. But anyway, does not depend on physical properties because absolute zero and triple point of water doesn't depend on physical or external physical properties. So if you use boiling point, right, boiling point depends on external pressure. So it will be affected by physical properties. So that one doesn't count. All right. Do a past year question now. Let's see if I can find a more recent one that has calibration. Okay. So set to dig a bit. Because it's been quite a while since they asked any of those questions. And I'm gonna look at the past year collections that you have with you, they don't have, I mean, I stopped at winter 19. I'm assuming May, June 20, there's no paper, but let me check. Let me check. May, June 20. Nope. See, the question is so cold that there are no recent questions. Very nice, I guess. So that means I have to do a very old question. But again, not emphasized. Because to be honest, the thermometer, if it doesn't work, you should read the manual. The manual will tell you that it can't work in certain conditions. So that awareness would help. Okay, nope. So recent years, 2020 has not come out at all from Feb March. Okay, I'll put a point here. So this first main idea about idea number 1, which is about thermometer and thermodynamic temperature. The last time it has not came out, none in 2020. So Feb March all the way to ON 20 didn't ask. Will they ask this year? I don't know. Like I said, I can't tell the future. You tell me lah. Do you think they'll ask? I don't know. Okay, but if I choose one question to do, that'll be very. I guess I'll do this one now. The last time it came out, I think, was May, June 16, paper 4.2. Okay, and then just in case you have no idea how to calibrate using the curve, I will do that one as well. So explain what is meant by the statement of two bodies in thermal equilibrium. This is a very basic understanding that when you see thermal equilibrium, it means that the temperature is the same. So this means that your both bodies have the same temperature and same rate of heat flow. To and from each other. Okay, so doesn't mean there's no heat flow, but the amount of heat flow is the same per unit time. Right? So suggest the type of thermometer to measure the flame of a Bunsen burner I've mentioned just now. This one I will use the resistance thermometer. The change in temperature in a small crystal when it's exposed to a pulse of ultrasound, this one must be very sensitive. So for sensitive thermometers, we would suggest something like the thermocouple. So those of you who do chemistry, you know that thermocouples are very sensitive, like, and you can adjust the sensitivity by adjusting the molarity. Okay, so you don't have to know how it works. Just know that this is a sensitive one, and then this is the one that can have large range of temperatures. Okay, some water is heated so that the temperature changes from this to this. State an appropriate number of decimal place, the change in temperature in Kelvin. So for this one, if you want to find the change in temperature, you can just minus lah. Okay, so the delta T here would be 38.0 degrees Celsius minus 26.5 degrees Celsius. So sometimes, right, the students will confuse between the conversion of degrees Celsius and Kelvin when it comes to change in temperature. And when they minus this and they get 11.5, not 12.5, 11.5 degrees Celsius, they tend to think to themselves, okay, I better convert this to Kelvin. So 11.5 degrees Celsius is equal to 11.5 plus 273.2. This is wrong. Then they write something in Kelvin. Okay, I add 273.2. So this is 284.7. This is wrong. Why? Because change in temperature is equal for both Kelvin and degrees Celsius. Because what you're going to do when you find change in temperature is for this 38 degrees Celsius, you will plus 273.2, and then you will minus 26.5 plus 273.2. You plus 273.2 minus 273.2, they go away. So they are the same thing. This can be 11.5 Kelvin. Okay, so this is just a note for you in case you don't know this. Change in temperature is equal for both Kelvin and degrees Celsius. Okay, the second thing that you should take note of is decimal point. So this one, think about the precision of your measurement. Okay, so this one has 1 decimal point. This one is 1 decimal point. So this one should be 1 decimal point. The change in temperature. Okay, final temperature in Kelvin. The final temperature is 38.0. If you want to convert this to Kelvin, you have to add 273.2. Okay, so by adding 273.2, this one would be 311.2 Kelvin. So when we convert Kelvin to degrees Celsius or degrees Celsius back to Kelvin, The full number, right, is 273.15. So when degree Celsius go to Kelvin is plus 273.15. Kelvin to degree Celsius is minus 273.15. Miss, how many decimal point to take? Follow the question. So if the question give you 2 decimal point, you take 2 decimal point. In this question, they gave me 1 decimal point. So for this one is 1 dp. So when I round 273.15 to 1 dp, I get 273.2. And then I substitute inside, and then I find the temperature. This question is 5 marks. The end, no more already. So if they ask thermometer, you expect about 4 to 5 marks. Not much difference, very easy if you know what to do. But it's also something where if you don't know, it's not that catastrophic. It's not as catastrophic as not knowing an entire chunk of gravitational field. Okay. All right. Regarding calibration, I'm just going to take the question right beside this. This is from, it's an old question because like I said, there are no calibration questions in recent years, although it is still in your syllabus. So this is a resistance thermometer. You're going to use it to measure changes in temperature from 12 degrees Celsius to 24 degrees Celsius. So you can see 12 is here, 24 is here. And the resistance is decreasing with temperature. Makes sense because this is a semiconductor. Yesterday, if you joined the review session for chapter 25, we talk about how changes in temperature can change the resistance of a semiconductor. Okay, so if we're talking about changing the resistance of a semiconductor, here, more charge carrier leaving hole behind, electron jump across the forbidden band into the conduction band. So you can see with more charge carrier at higher temperature, the resistance has dropped. State and explain the feature in figure 3.1 that shows that the thermometer has a sensitivity that varies with temperature. Okay, not resistance that varies with temperature because that is Captain Obvious, but sensitivity. Okay, so sensitivity here means the change in resistance over the change in temperature. Let's say this is theta. Okay, then this is R. So for example, if let's say we look at 12 to 14, when your temperature at 2 degrees Celsius, your resistance will drop how much? Resistance will drop from 24 ohm, 1000 ohm to about this value, which is 2130 ohm. 2130 is 2100 200300. So you can see that for the first increase in 2 degrees Celsius, okay, I'll write here. First increase in 2 degrees Celsius. So basically 12 degrees Celsius to 14 degrees Celsius. The change in temperature, this is your change in temperature. The change in resistance is 2400 minus 2130. 2, 4, 6, 8, 10. 2130. This is 270. Okay, let's consider the last 2 possible reading here. For delta theta from 22 degrees Celsius to 24 degrees Celsius. This one, this is 16245, so 1650 or 22 1650 to this value. This value is 1580. So it's 24 1580. The change in resistance is only 1580 or 1650 minus 1580. You can already tell that this is very small. This change in resistance is very small compared to this change in resistance, which is much bigger. But if you need numbers, I write numbers for you lah. Sometimes they need you to put numbers one. This is 70 degrees Celsius. Okay, so this is because the gradient of the graph is decreasing. And you can see, right, for the first 2 degrees, it's very sensitive. The resistance will drop by 270, so it's very sensitive. I can create a lot of marker in between here. But from here to here, it's not as sensitive already, because when the temperature change 2, the resistance only change 70. Okay, so you could say that the sensitivity varies with temperature. So at temperature of 12 degrees Celsius to 14 degrees Celsius, the resistance decreases by 270 ohm. At temperature 22 degrees Celsius to 24 degrees Celsius, resistance decreases by 70 ohm. The sensitivity, make your conclusion. Sensitivity of the thermometer decreases with temperature, is less at higher temperature. This is also seen because the gradient of the graph decreases as temperature increases. Okay. So this is what I mean by you provide proof from the graph, because they say explain the feature ma. So I use two proof. I use the coordinates and then I substantiate my proof with the gradient. I know it's only 2 marks, but I prefer to write in such a way where I won't lose mark, because you have to anticipate the mark scheme. So I've known that sometimes mark scheme, they want me to talk about the change in temperature and then how much the resistance change. So this is proof 1, evidence 1, exhibit A, and then here is exhibit B. And then you make your conclusion. Okay, sensitivity is lesser at higher temperature. All right, next. At a particular temperature, the resistance of the thermometer is 2040 plus minus 20. Determine the temperature to Kelvin to an appropriate number of decimal place. So 2040, you want to find 2040 is here. So if I drop all the way down from this line, I will get 15. Okay, 2040 is here. But they say 2040 plus minus 20. So plus 20 will be up here, because this is 2060. Minus 20 will be here, because this is 2020. The apocalypse here. So I think you can plus minus these two boxes. Let me zoom in a bit so you can see. Okay, so this is 2040. Your 2020 is down here. Look at where the curve is cutting the box here. Then this one here is 2060. So your plus minus, your error bar, your plus minus 20 is here. So the error bar plus minus 20 is here. This is the error bar. Okay, meaning the curve that we will take is from here to here. So if I'm going to highlight it, it will be these two boxes. So it will be 15 plus minus 1 box left and right. Okay, scroll the way down. 15 plus minus 1 boxes left and right. So it's 14.8. 14.8 all the way to 15.2. 2, 4, 6, 8, 10. Yes. So let me zoom out again. So the temperature is, let's do degrees Celsius first. So 15 degrees Celsius plus minus 0.2 degrees Celsius, because it was 14.8 degrees Celsius to 15.2 degrees Celsius. Okay, convert this to Kelvin, right? So this is not just 15, by the way. You want to write it in absolute uncertainty, then it should have to be 15.0. So now I'm going to convert to Kelvin. So conversion to Kelvin, we will take 15.0 plus 273.2. So this one would be 273.2. This will be 288.2 plus minus 0.2 degrees Celsius. And this will be your final answer. Why? Well, because you don't have to convert change in temperature in Kelvin. So you also don't have to convert uncertainty in Kelvin. Sorry, this is Kelvin. All right, so that is not needed. So this is the first type of question. They can ask you to convert temperature, read a calibration curve. Pretty straightforward stuff, as long as you know how to analyze the graph given. This thing is 2 marks. Okay, so if you read the right temperature, 15 degrees Celsius, and then you convert correctly, must convert correctly, yeah, you get A1. And then if your uncertainty is correct, you get another 1 mark. I think it's B1. Old mark scheme lah. Don't rely on this. This is May, June 2006. Some of you watching this may be younger or may not be born in 2006. Okay, so this is the thermo temperature question. Not very popular. Let's move on to slightly more popular territory, but also didn't come out in 2020. So the first idea here is temperature, okay, and thermometer and thermodynamic temperature. The second idea here is the specific heat and specific latent heat. So the idea of specific heat capacity and specific latent heat. This one is more popular because it's a calculation question. And they are quite repetitive. So if this one come out, it's actually quite the bonus. And did it come out last year? Let me see. I don't think so. If I look through it just now. Nope. Nope. So this one is also none in 2020. So would it come out this year? Again, I don't have a crystal ball. I don't know. Maybe this is more popular lah. More popular than the thermometer. I'm gonna do one question. But before that, let me tell you the equations you need to know in order to solve questions from here. You need to be able to, number one, define specific heat capacity and specific latent heat. Okay, the amount of heat required to increase 1 kg by 1 degree Celsius is specific heat capacity. The amount of heat required to convert 1 kg of a substance from solid to gas or from solid to liquid or from liquid to gas is specific latent heat. So since I opened the textbook now, I crop inside for you. Okay, so make sure that you know how to write the definitions if you intend to answer questions like this. No? So L is specific latent heat. I'm going to put this one here. Energy needed to change the state of 1 kg at constant temperature, because we know heating, cooling, all these happen, melting, all this happen at constant temperature, melting, boiling. And for specific heat capacity, this is the energy needed to raise the temperature of 1 kg of substance by 1 degree Celsius. Okay, so this is the definition for C. This is the definition for L. And right now what we will do is we will perform a series of state change. And I think you have seen graphs like this before. This one is pretty popular. So sometimes they can give you a graph, sometimes they'll just give you a table with values. So this is what we are doing. We are changing we're adding heat. Okay, so a certain different amount of energy will be absorbed at every step of the way so that there is a state change. Right, so that's it for this part. What are the equations you need to use? Okay, so the equations here are derived from the definition. Okay, so the definition of C is the amount of heat required to raise the temperature of 1 kg by 1 degree Celsius. Okay, or normally Q is equal to mc delta theta. Good news, there are no auxiliary or secondary equation that you need to. Yeah, there's one that you need to know. I will tell you that later. And then your L is equal to how much heat you needed to change the state of 1 kg. So Q is equal to ml. Okay, there are experiments for us to determine the value of C and L, but C and L is constants based on the type of material. So C and L depends on the substance. Even if it's the same substance like water, right? The specific heat capacity for water in liquid format and water or H2O in gas format is different. It's harder to heat gas up. It's easier to heat water up. All right. So this all depends on the substance. Next thing, when we do the experiment, normally we put it in some immersion heater or some heating devices, right? Let's say, for example, we put this inside a heater like this. If we want to melt ice, remember? Would they ask this in paper 5? Not really. Okay. So it's a heater, and then sometimes we'll put it inside a condenser. If you want to measure the specific latent heat of vaporization. Actually, okay. So notice that they are all connected to a circuit. This thing is to measure the specific latent heat of fusion because you are melting ice. So they're all connected to a circuit. If they ask you to draw the circuit, you should be able to draw, but you need to think about what kind of circuit are you drawing. Okay, so notice that number 1, the heating element is here. The heater is here. This thing will dissipate heat and boil the water. The heater is immersed inside here, so the heat will go out towards the ice and the ice will melt. Okay, so how much heat is being transferred? Q. This one transfer out is Q. To find Q, we will need to use the equation PT. Power of the heater multiplied by how long you turn the heater on. Makes sense, right? The longer you turn the heater on, the more heat will travel to the surrounding and do your change in temperature, change in state. Okay, but Q is equal to PT. Power of a circuit is equal to VI. Okay, so you need to know this because sometimes they will ask you, they will give you the ammeter and the voltmeter reading. So this is the voltmeter reading connected in parallel to the heater, And this is your ammeter reading connected in series. So ammeter is series, voltmeter is parallel. Series, parallel. Okay, real start is to adjust the current, so the current is always the same. Think about your paper 5, okay? So this VIT is important because we will use VIT to find Q. All right, understand that sometimes they will ask for rate of energy transfer, then you need to divide back by the time again. So it depends on the question. Okay, so with this, we can do some past years already. And since it didn't come out last year, I'm going to have to do something a bit older. Okay, let's see, which one should I do? I'll try to do one that is not recorded. So let me see what is recorded. Don't remember the we. Okay. We can do question from. Okay, so I would suggest that you, if you haven't tried yet, do the last time this one came out is ON19. So the variant 4.1 is already recorded, I believe, but let me check. Variant 4.1 is already recorded. Okay. So go and try first after you watch this video when you have time, and then go and use the recording if you need extra explanation. If not, then you're okay, you're good, no need to continue. So variant 4.1 question 3. This is recorded. You can watch it inside the playlist. Then we could try variant 4.2 because 4.2 is asking a similar question. Okay, so I'll do 4.2 now. If you haven't done 4.1 yet, go and do that. Go do. I'm gonna bring the question in. So normally when they ask you this one, they'll tell you some long-winded story about the experiment, which is fair, so take some time to read it. So here we have first the definition, what is meant by specific latent heat. That would be the amount of heat it of a substance at 2 marks, right, at constant temperature. So the constant temperature is the second mark. Amount of heat required to change the state of a substance is 1 mark. Whether it's, do you need to specify solid, liquid, or gas? No need, because this one is general. If they put vaporization, then it is liquid to gas, vapor ma. If they say fusion, then is solid to liquid. All right. So right now, they didn't say, so it doesn't matter. Lo. Constant temperature is the second mark. Okay, so get the definition out of the way. 2 marks in your pocket. Right now, we have a student using this apparatus. This is the same apparatus that I've shown you, 2D drawing. You see voltmeter is in parallel, ammeter is in series. Balance reading measures the mass of the beaker and the melted ice at the beaker. Heater is switched on, and pieces of ice at 0 degrees Celsius are added continuously to the funnel so that the heater is always surrounded by ice. So as the ice depletes, we will add more ice in. The water drips out of the funnel at a constant rate. The balance reading is noted. So at first, right, the dripping is not constant one because the heater is trying to achieve thermal equilibrium with the surrounding ice. So it will take some time. But once the thermal equilibrium is achieved with the surrounding ice or thermal contact, then the heat will transfer out at a constant rate. So basically we wait, okay? We wait for things to settle. The balance reading is noted at 2 minutes interval, and after 10-minute interval, the current in the heater is increased, and the balance reading is taken for a further 12 minutes. So this is a situation where they change the current twice to get two different readings. Because we always have to care about the environment. And in this case, the environment help you melt ice. I need to know how much ice is being melted thanks to the environment. Okay, so this is your ammeter reading. The second ammeter reading, we double the current. Voltmeter reading will change accordingly. Okay, will also increase. And you can see once the reading increase, this graph is steeper. Okay. So we're gonna question now. Let me crop it. Okay, part 1. From 0 to 10 minutes, 65 gram of ice is melted. Okay, so I'm probably going to use this later. 10 minutes, 65 grams is melted. Using the graph, determine the mass of the ice that melts from 12 minutes to 22 minutes. Okay, let's go back and stare at this. 12 minutes to 22 minutes. 22 is here, ma. Right? So it's just read the graph. So a lot of graph reading today. This one looks like 1, 2, 4, 6, 8, 10. So this is 4 for 10. So this would be early morning. My brain cannot. I shall use my calculator. All right, so this is 145. 12, 145, okay. And this 22 would be 285. 285, 145. So 285 minus 145. That will be 140 gram. This is what I mean by it's an easy chapter. Explain why, although the power in the heater is changed, the rate at which the thermal energy is transferred from the surrounding to the ice is constant. Well, your funnel is, the ice here is 0 degrees Celsius. I'm assuming the surrounding is constant, okay? The room temperature is constant. Maybe the room temperature is, maybe you sit in a MCKL lab, 27 degrees Celsius. So this temperature difference is the same. So the rate of heat transfer is pretty constant, although you don't learn the actual equation to find the rate of heat transfer. We didn't change anything. Okay, so what can cause this heat energy from the surrounding to the ice to increase is I make the room hotter, or I make the room colder, or I use a bigger funnel. I don't know, maybe the surface area of the funnel. So all these things, changing the physical conditions will change the amount of heat, the rate of thermal energy transfer. But right now, everything remains the same. So I would say this is because the temperature difference between the ice and the surrounding, which is the room, is still the same. All right, determine a value of the specific latent heat of fusion, 4 marks. And part 4, calculate the rate at which thermal energy is transferred to the surrounding. Okay, so they want L and then they want how much thermal energy is surrounding per unit time. Rate transferred from surrounding. So in this question, right, if you don't know, we have to do simultaneous equation. All calculation involving specific heats need simultaneous equation because there's a surrounding. Unless they very explicitly, very directly tell you that, oh, there's no heat transfer to and from the surrounding, or the beaker is very well insulated, or the funnel is well insulated. In most cases, no lah. We will take double reading, like this case, 2 reading. Okay, so what is the first reading? The first reading is the first 10 minutes. So the change in mass, this change in mass is 65 gram in the first 10 minutes. So in the second 10 minutes, after 10 minutes, this change in mass, you see, 12 minute to 22 minute is still 10 minute, right? So 140 gram. This is in 10 minute. This is also in 10 minutes. Okay? Because 12 to 22 is 10. They were trying to help you by suggesting a suitable time frame. Okay, you can take any 10 seconds between 12 second between where the gradient of the graph begin to change. So when did we change the, okay, after 10 minutes. But you notice 10 minute is here. Let me explain a bit to you first, the graph. 10 minute is here. The question, it says after 10 minute, the current is increased. Let's zoom in. Why doesn't the gradient of the graph change immediately? You got think about it. Why? Why like that one? Why here still the same? And then somewhere like maybe about 20 seconds later or some time later, then only the gradient becomes steeper. Like why does it take time for the graph to adjust itself although I changed the heater at 10 minutes? The answer is if you ever cook any food, there's this thing called carryover heat, meaning it takes time for the vibration to transfer or to change energy. So if they ask you why the gradient of the graph doesn't change immediately at 10 minutes, I zoom out so I can write. Gradient doesn't change immediately because time is needed for the ice and new hotter heater to get to know each other. No lah. For the ice and heater to achieve thermal contact. The vibration change, so it takes a while. Lag. It's the lagging of temperature. Okay. So this is why we cannot start the reading at 10 minutes. So if let's say they didn't tell you to take from 12 to 22, doesn't mean you can take from 10. Okay, so some students, they message me and then they say they start from 10 and then they cannot get the answer. That's why lah, because this part haven't become a straight line yet. It's still turning on the way. All right. So you should take it when the whole thing stabilizes into a straight line. So you can take 12 to 22. You could take 14 to 24 if you have reading, but the graph doesn't reach there. Okay. Or you could just take 5 minutes. You don't have to take 10 minutes one. So right now we have these values and we can now think about the conservation of energy. I'm going to crop the values and put them here for easy reference. Okay, so this one, think of conservation of energy. Right now, the ice is melting. What helps the ice melt? That is the heat from the heater. So I'll put Q heater, the heat from the heater, plus the heat from the surrounding. The surrounding will help you melt ice, what? No, you leave a cup of ice on the table and see melt or not. Will be equal to the heat needed to melt ice, which is ml. Okay, so first reading or the first 10 minutes. So for the first 10 minutes, the heater power would be VIT. So in case you need this, I will write this one here for you. Q is equal to VIT. So the first 10 minutes, the amount of heat from the heater will be 7.3 voltmeter reading, 1.8 ammeter reading. T, 10 minutes. Have to convert, miss. Yes, lor. This one SI ma. I mean, gram is not SI, but please convert, okay? So this T is 10 times 60 seconds. All right. Do you know the heat from surrounding? Don't know. I'm just going to call this QS. Okay. And this will be the amount of mass melted, 65 gram times L. I'm going to keep the gram because not Instagram, but this gram. I'm going to keep the gram because the final unit is in gram. But I have to convert everything here into SI because all of this is joule. All this will become joule. That's how you get joule per gram. But you got one equation and two unknown, right? The first unknown is QS. You don't know the heat loss to surrounding. The second one is L. In fact, for part 4, they ask you to find heat loss to surrounding. This is why we gave you a simultaneous equation or a double reading. So this is for the first 10 minutes. And then this is for the 12 minute to 22 minute. So for 12 minutes to 22 minutes, we're going to repeat the process again. 15.1 times 3.6 times 10 times 60 or 600 plus QS. Because it is the same time difference, so the heat loss should be the same. Right here for you. These two, QS, is the same, equal, because it's the same time interval. So the rate is the same. Rate is the same, the time interval is the same. Now we have more ice, 140, okay, times L. G is the unit lah. Okay, two equation, two unknown. How to solve? Simultaneous law. I want to get rid of QS. So the natural thing to do is minus. So label the equation 1, equation 2, and then I'll do something like, the easiest way is to just take 1 minus 2 lah, because I stacked them together already, right? So if I do 1 minus 2, let me settle this part first. 7.3 times 1.8 times 600. This will be 7884 minus. I know I will get a negative number, but I'm not that stressed about it. 32616. QS minus QS go away already. So this will be 65 minus 140, which is negative 75L. The negative will go away. You can find your L already. So 32616 minus 7884 divided by 75. This one is 329.76. I guess I can write this one as 330. Okay, in 2 to 3 SF. If they want it in joule per kilogram, then you have to convert this 65 and 140 to kg by dividing by 1000. So then the answer will be multiplying 1000. But the part is rudimentary. So this is why it's 4 marks. Okay. You starting with either with this equation is 1 mark. Okay. So you know that there's heat loss. Okay. If you know Q is equal to VIT with substitution, VIT, this is C1 mark. Simultaneous equation, some simultaneous equation working is C1 mark. Final answer is A1. Okay, so the simultaneous working have to be obvious lah. The examiner should know what you're doing. Sure, you can use substitution by moving the equation around. That is also okay. But 1 minus 2 is easier lah. QS just goes away. Okay, so right now you're asked to find the rate of thermal energy transferred. So this will be QS over T. find QS first law. So I'm going to substitute L as 329.76 into, let's say, into equation 2. You can use equation 1 or equation 2, it doesn't matter. So 32616 plus QS is equal to 140 times 329.76. Dun, dun, dun. 2616. This one is 13550.4. But you need to divide by time, right? So hence the rate, right here, hence rate is equal to QS over T. So 13550.4. The time is 10 minutes, 60 for a second. So divide by 600. This is 22.58. So I guess I can put 22.6 or 23. So finding QS is 1 mark, C1. Then you divide by 60 times 10. This is your A1. So this is how you get the 10 marks now. There is some form of simultaneous equation. All right. I am not going to do the rest already because they're all about the same. You should try some that involves specific heat. Specific heat capacity is not that popular. They like to ask you to find the latent heats. So this thing came out again in ON18 paper 4.2. So you can try lah. Try ON19. Just now, what question did I suggest? ON19 paper 4.1 is already recorded. Okay. ON18 paper 4.2. These are all question 3. Why is my handwriting so bad this morning? What happened? Write too much now. Recorded. Question 3 is not recorded. You go and try lah. They are. I want to say they are all the same because they are in my brain, but maybe not to yours. So you go and try first and let me know. So it was very popular for a while, and then it kind of like fall off the viral trend, the bandwagon. So go and try this question. These two, I think it involves ice. This one involves boiling water. Okay, so you do them and you compare the difference. Next one that you should do. This one is a bit hard, but ON12 paper 4.1 question 3. Okay, not a bit hard lah. It's just different. This is not heating, not boiling water, but heating water. Okay, so I think this is enough for you to get a glimpse of how the question can look like for this part of the situation. This too is heating water. Dun, dun, dun. FM16 P4 question 3. So since 2020 didn't come out, 2020 only asked guess, I expect maybe they'll ask again this year. Likely lah, but cannot say for sure lah, because previously every year they will at least ask either in ON or May, June. But just looking at the past year collection, they haven't asked for a while. All right. So use that information as how you will decide how you want to operate. Okay. There's one more example that I will not talk about because it's already recorded. But if you haven't, go and study May, June 18, paper 4.2. The ice in the cup. Okay. So for a while, because long time didn't come out, I think the last time this one come out was 2008 or 2006 or something far away. Then people tend to think, oh, won't come out already lah. But Miss Lee will throw in old questions. Who knows, man? I got insecurity lah. I got trust issues. Maybe it will come out. So I will suggest you go and study this one. It is already also recorded. Okay, so now the ice will melt, and when the ice melt, what is the final temperature? I think they will talk about the final temperature of the water, etc., etc. Go do this one. Is there any similar one in the recent years? Nope. This one was the last time it came out. But if you want something similar or very close to this one, after you watch the recording, you want to practice, then you will practice May June 07 paper 4. Question 2C. Because I think, well, let me confirm first. And also, ice, these are all ice in cup question. Ice in a cup. Sounds like a very bad Netflix show. Ice in a cup. Okay, May June 10, paper 4-2, question 3. This one is a bit different, a bit unique because let me show you. It start with a temperature. Go try this temperature question first. Okay. Then after that, there's a cup. So I think the last time this one came out was May June 10. And then it was quiet for a long while before it makes an appearance again. So you should go and try the question. And then if let's say you encounter problems in the next review session before we start the recording, I can discuss them with you. But yeah, I think good enough lah. Just try this. So all this is about specific heat, specific heat. Here to here is L. Here to here is C. This one is C plus L. Ice is going to melt what? All right, so the ice will melt and something will happen. So read the question. This is recorded. Hopefully when you watch the recording already, you can answer these two questions. So here is where we have ended this part of the map. Okay, so the part of the map here where we talk about how to measure temperature, what is temperature and heat, and the temperature will change the state of the matter. So either you use MC theta or MC delta theta for specific heat capacity, or ML for change in state. Okay. The next part of thermal physics, which is the more popular section or the most popular section, would be about gases. Because after you change your state, right, now you are talking about gas already. And we all know that when temperature increase, the kinetic energy will increase, because when you heat something up, the particles will vibrate faster. So now we need to zoom in and look at the particles. What happens to the particle? And we need to zoom in and look at the bond. What happened to the potential energy? So for specific latent heat, whenever there's a state change, you weaken the bond. It's like stretching a spring. The potential energy will increase. So there's this part where it's so rarely asked that I didn't mention, or I couldn't find a past year question in front of me to remind myself to mention that there's a solid liquid gas and you should compare the KE and PE lah. Okay, that one you can refer to your notes. Great. We can move on to gases now, but I think I will stop the recording and record a second video for gases.